Okay, bonjour, hello, good afternoon. Welcome to the second session of this workshop dedicated to the memory of Xavier Le Pichon. In this session, we're going to go down to Earth, basically, from the broad overview that we had this morning of the rocky planet system to our own Earth. And the session is dedicated to dynamics, mantle dynamics, which is a topic that was also of great interest to Xavier Le Pichon. As you will see, I will mention some things about this. So, as you know, we have this cartoon. Why do we have plate tectonics? Something must be moving inside the Earth, some convection currents. This is a cartoon. It's certainly not very precise or very accurate, but the main idea is that the Earth is losing heat, and to very first order, you can think about it as fluid heated from below, although in reality it is also heated from within. And if you have a core bobbing at the top, it will be moved by the convection currents. So there are many questions that remain open about the Earth's interior and its dynamics. What is the proportion of internally heated part of the energy? And what is the proportion of heat coming from the core, coming from below? This gives rise to very different planforms of convection. And so geodynamicists with increasingly powerful computational resources are trying to model what can be happening in the Earth. So geodynamicists are doing this numerically, like in this example, and also experimentally, as we will hear. And to investigate this, you can have all these geodynamic models, but they have to be constrained by some observations. And among the observations that are the most relevant and powerful are the observations from seismic imaging of the Earth's interior. And so seismic imaging is like medical imagery. Basically, you have sources of waves on the surface of the body, and you record them on the surface of the body elsewhere, and from measuring some of the properties, you will be able to back project and image the structure. So in seismology, we use seismic waves that travel across the Earth's interior from earthquakes to distant stations. And we primarily measure their travel times. And by back projection, we can back project to where the anomalies in travel times with respect to a reference model have originated. And we have this color convention where blue indicates faster than average regions where the waves are the speed is increased, and then red is where the speed is decreased. And to first order, we can translate this into anomalies in thermal anomalies, anomalies in temperature. This is not the only thing that matters, because compositional differences are also important. But to first order, you can think about when you see blue, it means colder, and when you see red, it will be hotter than average. In seismology, we have another constraint, is that we are limited to natural sources, large earthquakes that produce waves that can travel long distances through the Earth, and also, and which happen only or primarily at the edges of tectonic plates. So the distribution is non-uniform, and also the distribution of stations is non-uniform, because we even though in the last 40 years, through many efforts in many countries, the density of seismic stations of high quality broadband seismic stations has increased tremendously. They are mostly located still in the continents, and so 2/3 of the Earth is not very well covered. So these are actually the main challenges in this field. However, there are many waves going through the Earth, and they bounce around the surface, the core mantle boundary, and other discontinuities in the Earth. And so if you can combine the information from all these waves, you can increase the illumination. And this is what has been happening in recent years with the advance of powerful computers to improve the resolution of images. But I like to start with this figure, which is one of the first. It's a map at 100 kilometers depth of shear velocity perturbation with respect to the average velocity at that depth, which is built from primarily the study of surface waves, so waves that travel along the surface of the Earth. And if you look at this figure, you can see already to first order, most of what you expect to see just from what you know from tectonics. You see and 25 years later, the same group produced a higher resolution map, but essentially the first order features are already there. But you can see the ridge system, where you expect new plates to be formed, so hotter than average. You see the cold cores of the continents, and also you can detect this color from red to blue here in the Pacific plate, which expresses the cooling of the Pacific plate. If you compare this to the age of the oceans, it is quite remarkably similar. And to me, this means that tomography works, because you're seeing what you're expecting to see. But it's also, in a way, a proof of plate tectonics, right? Because what you're seeing is really symptomatic of what plate tectonics manifestation. And here is just a plot of the structure as a function of age of the Pacific plate to just make, this is age in millions of years, and this is depth to show how the structure changes as the age increases, essentially the cooling of the plate. And so this is isotropic velocity, so it shows you basically the structure in shear velocity independent of direction. There's another measurement which I want to mention right away because I won't talk about it much more, is the so-called anisotropy. The seismic waves, it turns out, don't travel at different speed in different directions, and the patterns that you can resolve from that are actually very important for constraining the motions, the dynamics. So here we see an example of so-called azimuthal anisotropy at 50 kilometers depth, where the little bars here indicate the strength of how strongly anisotropic the structure is, and the orientation indicates the orientation of what we call the fast axis, which direction the waves are traveling the fastest. And if you compare this to the plate motions, here the plate motions that have been derived from ancient motions, so fossil absolute plate motion directions, you see a lot of correspondence. I will emphasize this direction here in the old Pacific plate, which manifests that what seismology is seeing at this depth is basically frozen patterns of motion in ancient times. So it can provide, even though we get mostly a picture of what's happening today, seismology can also provide some information or some constraints on past dynamics. At 150 kilometers depth, the pattern changes, and in fact, you can see, especially if you focus on the Pacific plate here, that the direction of the fast axis is aligned with the absolute plate motion, current absolute plate motion direction. So basically, we've moved to the lithosphere, which has the frozen system, to the asthenosphere, which is presently deforming and which is reflected in this seismic anisotropy. Another kind of important kind of early realization, which I like to show, is this is now we're now going to the very deep mantle. So this is 2,500 kilometers depth. So it's 400 kilometers above the core mantle boundary, and it is a color representation of, I guess, the first or very first models of. This time it's compressional velocities obtained by inversion of travel times of P waves. And already then it was apparent that at the base of the mantle the structure has completely changed. It has not much to do, at least apparently, with plate tectonics. And you have this ring of fast velocities surrounding two regions of low velocities. And at that time, these authors realized that this was very similar to the observed geoid, except that the sign was reversed, so that the low velocities corresponded to highs in the geoid, and the high velocities corresponded to the lows in the geoid, which is the opposite of what you might expect if you just translated velocities to densities, because the cold regions where you have fast velocities would correspond to cold material and therefore denser, so you would expect high gravity. And correlation coefficient, even at this very long wavelengths, was quite high, and remarkably, the authors proposed two possible explanations. One related to differences in composition, lateral variations in composition. So to explain the regions of fast velocities but low gravity, they invoked the presence of eclogite, which would be related to subduction, to subducting plates, and ending at the core mantle boundary and producing these laterally heterogeneous patterns that are viewed in the seismic models, or a dynamic interpretation due to the presence of convecting currents in the mantle, which would cause deformation at the Earth's surface. And so if you have a rising current, you expect the surface of the Earth to be deformed upwards, and therefore you would get above a rising hot current, you would get a high gravity, high geoid. So why I show this is because these debates are still occurring. Well, first of all, this dynamic interpretation, of course, led to the realization that the mantle is viscous and that you have to include this non-infinite viscosity in the modeling, but it is still debated that whether these structures down there are purely thermal or compositionally different. So to summarize what the status was about almost 20 years ago, if we go down the mantle from the top, we already discussed this, to the bottom, as you go down at the base of the upper mantle, the structure has changed, and you're primarily seeing the subductions, the subducted slabs. You have the signature of the subducted slabs. And here are some depth cross-sections across these regions showing the behavior of these slabs as they go down. At 1,000 kilometers, there's even less signal, but still, very importantly, actually, you see these slabs in some regions that are ponding around 1,000 kilometer depths. One expects the slabs to pond around 660 kilometers, which is a phase transition, a mineralogical phase transition. So you expect that you might have also a rheological transition. But at 1,000 kilometers, it is still not clear what might be causing it. And I'll go back to this a little later. And then at the bottom, you have, as I mentioned already, the slab graveyard, which is surrounding these two regions equatorially located, more or less antipodal, which have the terrible name of large low shear velocity provinces, LLSVPs. Talking about relations of seismology to dynamics, the models are becoming accurate enough that you can start tracing the subduction or subducted slabs down into the mantle as they sink and sort of relate the images, the seismic images, to the position of these slabs that started subducting some millions of years ago. And so in this particular study, we see here these traces of the so-called Farallon subduction, which has reached mid-mantle depths, and on the other side of the world, the Aegean subduction, both of them on the order of 200 million years old, and also some evidence for some older slabs down in the mantle. And so this is, of course, an interpretation, but it has been used to help constrain the longitude of tectonic reconstructions to match basically the position, the current position in the deep mantle of these slabs. So now, talking about the low velocity regions, the large low shear velocity provinces, these are three models from 20 years ago, where you can see this is almost right above the core mantle boundary. You can see that in their large scale pattern, they are quite consistent. So much so that in this map, which is not a tomographic map, it's a voting map, which consists in determining which models agree that the structure is faster than average and which agree that it's slower than average. You can actually reconstruct even the borders of these anomalies quite well. These anomalies are not compact like this. This is just an artifact of this being a voting map that has filtered models. But anyway, I won't go into the details. If you only look at the longest wavelengths of these patterns, you find remarkably that this ring of fast velocities contains the pole of rotation of the Earth and also the paleopole positions for the last 200, maybe 250 million years, and that the LLSVPs are located equatorially and antipodally, which suggests a stable pattern from the point of view of the moments of inertia of the Earth, and also basically is reminiscent of this very simplest degree 2 convection in a sphere, right, with two upwellings, two opposed upwellings, and one downwelling in the middle. There's also arguments about the position of large igneous provinces, sorry for the typo, being at the edges of these LLSVPs, and all of this suggests that a certain stability, that the LLSVPs may have been stable for at least 250 million years. So the LLSVPs, whatever they are, whether they're compact, and I actually don't think they are compact, but the position of where the subduction zones happen and where the upwellings happen may have been stable for quite a long time. And so this brings up some work by Xavier Le Pichon, already a long time ago, 1984, where he had basically noticed that 200 million years ago, if you look at the distribution of continents in Pangaea, that it actually fits in a hemisphere. This is like a great circle of the Earth, and so one hemisphere contains completely the position of the continents and surrounded by subduction zones. And he noticed also the correspondence with the geoid, with the geoid high in the middle of the same great circle. And 20 years, no, 40 years later, we had a workshop on to celebrate the 50 years, I guess, or how many years of plate tectonics, and Le Pichon presented, a sort of updated version of this in color this time, where basically which confirmed this pattern, and again with the geoid. But in addition, now he had this opportunity to look at these tomographic models, these seismic models, and this is again a voting map. This is not a real tomographic model, but it shows at the base of the mantle the LLSVPs here centered on Africa, with the continent outlines here at the present time and reconstructed 200 million years ago. And he argued that there has to be some kind of non-random link between this position of these features and the way the continents were kind of distributed at the time of Pangaea. Let's continue. So now we're looking at the base of the mantle, and we're going a little bit further in time in terms of tomography. I told you I didn't like the idea that the LSVPs are compact. In fact, this model, which we built 10 years ago, shows that they're full of holes, and they are basically the location of the roots of many very large mantle plumes. Here is an example in Hawaii, but this model showed the presence of these very broad plumes, and all these plumes essentially that are so large and so visible, that span the whole mantle, and certainly up to the upper mantle in a relatively straight fashion, and then meander in the upper mantle. They're all located, have their roots located on the LLSVPs. There are other hotspots, of course, and yes, and they're all associated with some hotspot mid-plate volcanism. There are other hotspots and maybe other plumes, but these are strikingly located above and these models have been kind of verified, different groups. Here, one example, cross-section from the surface to the core mantle boundary across near Samoa, the Samoa hotspot, two different models. This is a model, more recent model from a group at Princeton. Here in the African hemisphere, Cape Verde, same, the details kind of change, but it is still very similar. So I want to spend just a few minutes saying what the striking characteristics of these plumes. They're rooted in isolated patches of very strong velocity reductions, inside which many of these plumes have been already shown to contain so-called ultra-low velocity zones, so very large zones of about diameter of 800 to 1,000 kilometers and thickness of about not more than 40 kilometers, with extreme shear velocity reductions like 30%. And we're seeing them more and more. We see one in Hawaii, Iceland. I mean, this is, of course, a collection of different studies. And more recent studies by different groups have shown their presence under many hotspots. We can't really verify that it's a common feature everywhere because the illumination is not favorable everywhere. But anyway, I will skip this. This is how we detect them. This is forward modeling of seismic waves. The other characteristic is that something happens at 1,000 kilometers depth. Just as slabs pond at 1,000 kilometers depth, something happens to plumes. Most likely, they become thinner and therefore less resolvable by tomography. But you can see this here, and this is reminiscent of what you might expect in a mantle a fluid where you have a jump in viscosity with lower viscosity in the upper part and higher viscosity in the lower part. And in addition, these plumes could be thermochemical. I'll talk about it again. But they are very straight in the lower mantle, so which means there's not much mantle wind in the lower mantle. And again, are things really happening at 600 kilometers or deeper, or is there a transition zone between 600 and 1,000 kilometers? More recent modeling kind of shows this again quite nicely. These plumes going up to 1,000 kilometers and then flattening out and then kind of going around, perhaps kind of suggesting the presence of secondary scale convection in the upper mantle. This is, and then what happens to them at very shallow depths is they connect to streaks, these kind of fingers, which we call fingers, which are streaks of very low velocities that are more or less regularly aligned every 1,800 to 2,000 kilometers. And you can find groups of plumes that feed these systems, which also have expression in the dynamic topography, in the residual topography of the surface. So this model is not your classical plume model, which in a thermal fluid you would expect a thin stem and a broad head. So something else must be going on, either a thermochemical plumes, as already kind of discussed at the very beginning, the possibility of feeding the remnants of lithosphere and the basaltic crust into plumes going up, which would give different shapes to plumes, or some other mechanisms such as basically a nonlinear rheology, which is also a possibility for the Earth's lower mantle. This deflection of slabs and plumes around 1,000 kilometers depth is seen both for plumes and for subducted slabs, and must have a reason. And this leads to this very kind of not very, maybe not that great a cartoon, but basically expressing that there are things that we still need to understand in the Earth, probably very different properties in the lower mantle defined maybe by its continuity at 1,000 kilometers and more vigorous convection in the top. So to finish, I want to tie into Xavier Le Pichon's work again, which is that if plumes are not the classical plumes, how do we explain the existence of or presence of flood basalts, which are these enormous outflows of volcanic outflows that have happened at different times in the world? If there is no plume head, what is happening? And in his paper in 2019, Le Pichon pointed out that, and you probably can't see this, that these flood basalt areas, which are those large magmatic provinces, are here concentrated inside these Pangea region, and that it is possible that the Pangea was basically acting as a heat blanket, which the plumes accumulated their material in the uppermost mantle until basically they started breaking up the plates. So I just want to point that out. I mean, it's been proposed by other people, but since we're talking about Le Pichon, I wanted to point out that he had views not only on the plate tectonics, but also on the relation with the deep dynamics. Okay, so today we have this session on global geodynamics, and it's a vast topic, many different aspects that could be covered. We can't cover all of them, but we're going to have a couple of talks which we can move on to directly. And so I would like to invite Anne Davai to come and present her talk, which is the necessary conditions for plate tectonics, convection in complex fluids. Okay, thank you.